Hi everyone. Let's talk about the closed interval method, a method to find absolute maxima and absolute minima of continuous functions on a closed interval. In the first exercise, we're given three functions, and we must determine where these functions attain their absolute maxima and minima. If you would like to try this exercise on your own first, stop the video now and download these notes using the link in the video description. Absolute maximum of a function is the largest value the function takes. Absolute minimum of a function is the smallest value the function takes. In the first example, the largest value the function takes is 2, and the function takes the value of 2 at -3. Absolute maximum is at x equal to -3. The absolute minimum of this function is -3, and the function takes the value of -3 at x equal to 3. In a second example, the absolute maximum of this function occurs at -1. The absolute minimum of this function occurs at -3. In the last example, the absolute maximum of this function is 2, and it occurs in 3 different places. It occurs at x equal to -2, at x equal to 0, and at x equal to 2. Absolute minimum of this function occurs in 4 different places. It occurs at -3, -1, 1, and 3. These functions attained their absolute maxima and minima at 2 different types of inputs. They attained their maxima and minima either at the endpoint of the interval or at a critical number. At the endpoint of the interval or at the critical numbers. If you don't know what critical numbers are, in the video description, I will add a link to a video where I explain critical numbers in detail. Closed interval method uses the fact that continuous functions on closed intervals can attain their absolute maxima and absolute minima at only 2 different types of points, at the endpoint of the interval or at critical numbers. The closed interval method says that if you want to find absolute extrema of a continuous function on a closed interval AB, you need to follow 2 steps. First, you find all critical numbers of the function in the closed interval. And then you evaluate the function at the critical numbers and at the endpoint of the interval. The largest value you get in step 2 is your absolute maximum, and the smallest value you get is your absolute minimum. Let's see how this method works in practice. In the next exercise, we must find the absolute maxima and minima of the following function on the interval from 0 to 2. If you would like to try this problem on your own first, stop the video now. This function is a polynomial, which means this function is continuous everywhere. In particular, it is continuous on the interval from 0 to 2. Because this is a continuous function on a closed interval, by the extreme value theorem, this function will attain its absolute maximum and its absolute minimum on the interval from 0 to 2. By the closed interval method, I know that those absolute extrema and minima will occur either at the endpoint of the interval or at a critical number inside of the interval. Let us first find all critical numbers of this function inside of the interval from 0 to 2. To find critical numbers, first I find the derivative. I use the power rule and I get 6x squared plus 6x minus 12. Then I ask myself 2 questions. Are there any x's for which this derivative does not exist? And I ask myself, are there any x's for which this derivative is 0? This derivative is a polynomial, which means it is defined everywhere. There are no x's that make this derivative not defined. The first condition gives us no critical numbers. To determine where this derivative is 0, first let me factor 6 from all the terms, and I will get 6 times x squared plus x minus 2 equals 0. Let me factor this even further. I get 6x plus 2x minus 1 equals 0. There are two x's that make this 0, x equal to negative 2 and x equal to 1. Out of these two critical numbers of the original function, only one of them is inside of the interval from 0 to 2. It is x equal to 1. That is the only critical number I will take into consideration. According to the second step, I must now evaluate my original function at critical numbers and at the endpoints of the interval. The endpoints are 0 and 2, which means I must evaluate f of 0, I must evaluate f of 2, and then f of 1, the value of the function, at the critical number inside of the interval. When I plug in 0, the first three terms disappear and I get simply 6. When I plug in 2, I will get 16 plus 12, that's 28, minus 24, that's 4, plus 6, that gives me 10. When I plug in 1, I will get 2 plus 3, that's 5, minus 12, negative 7, plus 6, negative 1. Now ask yourself, out of these three numbers, which one's the biggest? 10 is the biggest, which means that according to the closed interval method, this is the absolute maximum of this function on the interval from 0 to 2. The smallest value is negative 1, which means negative 1 is the absolute minimum of this function on the interval from 0 to 2. Absolute maximum occurs at the endpoint. Absolute minimum occurs at the critical number. Let's try one more problem. This time, we must find the absolute maxima and minima of the 7th root of x on the interval from negative 1 to 1. If you would like to try this problem on your own first, stop the video now. I follow the same idea. First, according to the closed interval method, I must determine the critical numbers inside of this interval. To find critical numbers, I take the derivative. First, let me rewrite the function so that it's easier for me to take the derivative. The 7th root of x can be rewritten as x to the power 1 over 7. This means that I can use the power rule to take the derivative, and I get 1/7 x to the power negative 6 over 7. I can rewrite this even more, and I can write it as 1 over 7 times x to the power 6 divided by 7. Now I ask myself two questions. Are there any x's for which this derivative does not exist? And are there any x's for which this derivative equals 0? I believe there is one x for which this derivative does not exist. I cannot plug in 0 to this expression, because if I did, I would be dividing by 0. X to the 6/7 power is 0. So I will be dividing by 0. I cannot plug in x equal to 0 there. A critical number, x equal to 0, is there. What's more, x equal to 0 is inside of the interval from negative 1 to 1, which means this is a critical number I will take into consideration. Are there any x's for which the derivative equals 0? I believe there are no such x's. If you were going to plug in some number, you were never going to get 0. Another way to see it is you can multiply both sides of this equation by the denominator. When you do that, multiply both sides of this equation by the denominator, you will get that 1 equals to 0, which is obviously nonsense. This equation has no solutions. Now, I follow the second step of the closed interval method. I evaluate my function at the endpoints of the interval. The interval was from negative 1 to 1, so I evaluated at negative 1, I evaluated at 1, and I evaluated at the found critical number. When I plug in negative 1 to my original function, 7th root of negative 1 is negative 1. 7th root of 1 is 1. And 7th root of 0 is 0. Negative 1 is the smallest number, which means this is your absolute minimum. 1 is the largest number, which means this is the absolute maximum. Both absolute minimum and absolute maximum occur at the endpoint of the interval. This should not surprise you. The function 7th root of x looks like the following. Makes sense? It makes sense that the absolute maximum should occur at the endpoint and absolute minimum should occur at the endpoint. There is a critical number at the origin because the function becomes nearly vertical there. The derivative does not exist there.